Hi, and welcome to Chapter 10. In this first section, we're going to go over radicals and radical functions. I think some of this will be review, specifically ones like the first problem, square root of 25, but other parts of this will probably be new to you because we're going to expand on what you previously have learned in grade school. Okay, when you take a square root, you take what's called the principal square root. Okay, that's typically what you'll see. The other one is called the negative square root of a. For example, the principal square root of the square root of 25 is 5. Now the negative of the square root of 25 would be negative 5. We're rarely going to use that, okay? Square roots are defined to be the positive number. Okay, so one fact that students often find confusing is the fact that although 5 squared equals 25 and negative 5, if you square negative 5, you'll also get 25. Although both of those numbers squared equals 25, the square root of 25 is defined only to be the principal square root. It's only the positive number. Okay, when you take the square root of a number, the answer is only the positive one. It's just defined that way to make this all mathematically possible and to make it so that square root functions are in fact functions. Okay, square root of 0, you would ask what number squared equals 0? Well, 0 squared is 0. So square root of 0 is defined and it is 0. The square root of 9 over 25. You're going to have to think in terms of fractions. What fraction is there so that when you square it, you get 9/25. Now remember, when you multiply two fractions, you multiply across their numerators and across their denominators. So therefore, 3/5 would work, and that's because 3/5 squared is equal to 3/5 times 3/5, which is 9/25. Okay, for square roots of decimal numbers, it's the same process. What decimal number squared equals 36? Well, this one you can figure out if you remember the square root of 36. Now, the square root of 36 is 6. So you know it's going to be something along those lines, close to 6. The question is probably in your mind, is it 0.6 or is it 0.06? Let's try 0.6 and see what happens, and let's check our answer. 0.6, if we square that and multiply it times 0.6, remember you multiply the numbers, so you get 36, and then however many decimals there are past the decimal number, that's how many units you move over your decimal. So that does in fact equal 0.36, therefore the square root of 0.36 is 0.6. Okay, for the square root of x to the 10th, now here's a tricky one. You want to ask what squared will equal x to the 10th, and that's a little tough, but and it might involve some guessing and checking. Okay, so let's do a guess here. When you multiply two numbers that have the same base and different exponents, remember, for example, x, this is just an example off to the side, so I'm going to write it up here at the top. Say you multiply x squared times x cubed. Remember, you add those exponents to get x to the 5th. So if you're trying to multiply something times itself and you want to end up with an exponent of 10, then you need two numbers who add to 10, and those two numbers have to be the same. So it must be x to the 5th, because x to the 5th times x to the 5th does equal x to the 10th. So therefore, another way of writing this is x to the 5th all squared equals x to the 10th. So the square root of x to the 10th would be x to the 5th. Okay, this next one has a number and a variable, but the same process applies. Okay, square root of 36 times x to the 6th. You would ask what quantity squared equals that? Well, we know 6 squared is 36, so that's part of it. And then the variable, as you can tell from this other problem, must be half of the exponent, so it must be x cubed. That way when you square it, okay, remember when you square 6x cubed, the square goes to everything inside. It goes to both the 6 and the x cubed. So that means 6 squared times x cubed squared, which is 36. When you have something like this, remember you multiply those exponents 3 times 2, so you have x to the 6th. So that does work. Okay, this next one says the negative of the square root of 25. The negative is not under the radical. This really means negative 1 times the square root of 25. That's another way to think of it. So you find the square root of 25, which is 5, and multiply that times negative 1 to get negative 5. This next one, though, is different because the negative is underneath the radical. And this one you ask, now what number squared equals negative 25? And if you think about it, you realize quickly that there is no real number because, as we already showed up here, 5 squared is 25, and negative 5 squared is also 25. So if you square a positive number or if you square a negative number, you're going to get a positive number either way. So this has no real solution. It's not a real number. And sometimes in your calculator, some calculators will say NaN. Okay, if your calculator says that, it means not a number. So you might get that depending on what kind of calculator you have. Okay, next let's look at approximating roots. First I want to talk about what is the difference between a rational and an irrational number. Okay, a rational number, this is just terminology that you need to know, is any number that can be written as a fraction or with a repeating decimal. So for example, 3/7, that's a fraction, or 0.252525 on forever is a repeating decimal because there's a pattern here after the decimal that repeats. That 25 goes on forever, which is you can indicate with a bar over those two numbers. The reason both of those are rational is because actually any repeating decimal can be written as a fraction, which we're not going to do, but you can do that. Irrational numbers are any numbers that are not rational. So for example, pi is not rational because it's 3.14159 and it goes on forever and the decimals never repeat. It's just a random pattern. Another number is e, the 2.718, and it goes on forever with no pattern as well. Square root of 2. Actually, a lot of square roots are irrational. Square root of 2 is approximately 1.41421, and it goes on forever. It doesn't ever repeat. So that gives you an idea of some rational versus irrational numbers in case I use that terminology. Okay, perfect squares, this is another word you need to know. Those are numbers whose square roots are rational. So for example, 25 is a perfect square because its square root is 5, and 5 is a rational number. 1/36, that's a perfect square because its square root is 1/6, which is a fraction. 1 is a perfect square because its square root is 1, which is rational. You get the idea. You could actually list them all out. 1, 4, or list all of the whole numbers out that are perfect squares. Because 1 squared, 2 squared, 3 squared is 9, 4 squared is 16, 5 squared is 25, and you can go on like that. So those are all perfect square numbers. Okay, for numbers who are that do not have a perfect square, never mind what I just said. For example, since there's no rational number whose square is 3, the square root of 3 is irrational, right? Because there is no whole number whose square equals 3 exactly, so its square root must be irrational. Now you can approximate it with a calculator, and that's the most common way to do it. Back in the day they had to look them up in tables. And in this case you'd get 1.73205. Okay, now if you don't have a calculator handy and you just need a really rough approximation, there's a simple way to approximate square roots, and that is using perfect squares. Okay, so you look for two numbers that 3 is between that are perfect squares. Well, 3 is between 1 and 4, which are both perfect squares, so you can say 3 is between 1 and 4, And so therefore the square root of 1 must be less than the square root of 3, which must be less than the square root of 4. Right, if you take the square root of all three parts here. So 1 must be less than the square root of 3, which must be less than the square root of 2. Square root of 4 is 2. So what that tells you is roughly the square root of 3 is between 1 and 2. Alright, so that's just a real rough approximation, you can say. So the square root of 3 is between 1 and 2. And it is. That is what we approximated, 1.7. Okay, that's square roots. Now this may be new to some of you. This is cubed roots. Okay, if cubed roots are numbers who, when you cube a certain number, that's what you get. For example, 2 cubed, that's 2 times 2 times 2, is 8. So therefore the cubed root of 8 is 2. Okay, that's what a cube is. Now that little 3 there, it's supposed to be written inside the radical like this. Okay, it doesn't mean 3 times the square root of 8 or anything like that. It's read the cubed root of 8. That 3 is a part of the radical. In fact, when we do square roots, we typically don't write a 2 there, but you could write a little 2. Okay, that's the same thing as the square root of 9 or 3, right? But the little number that's there in that little piece or that little area right above the radical, that tells you that's called your index, okay, and that tells you what root it is you're taking. That's called your index. Okay, the cubed root of negative 8. Ask yourself first, before you say there is no answer, is there a number whose cube is negative 8? So that when you multiply it by itself 3 times, you get negative 8. Well, we know that 2 cubed is 8. So let's try negative 2. If we do negative 2 cubed, that's negative 2 times negative 2 times negative 2. Well, 2 of those negatives cancel, but you're still left with a third negative. So that is, in fact, negative 8. So therefore, the cubed root of 8 is actually negative 2. Okay, so because you're taking a cubed root, and that's an odd number, so only 2 of those negatives cancel, you can actually take the cubed root of a negative number. Okay, cubed root of 0 is just like square root. 0 cubed is 0, so the cubed root of 0 is 0. With fractions, you would ask, what fraction is there whose cube is 1 over 64? Well, the cubed root of 1 is 1, so we know it's going to be 1 over something. And then you have to ask, what number cubed equals 64? And sometimes these may take a little practice to get. But if you try a few numbers, you'll figure it out pretty quick usually. Okay, 2 cubed is 8. 3 cubed. 3 cubed would be 3 times 3 times 3, which is 27. Next, let's try 4 cubed. 4 cubed is 4 times 4 times 4. Well, that's 16 times 4, which is 64. So 4 cubed is 64, so the cubed root of 1 over 64 would be 1/4. Okay, the cubed root of x to the 9th. Let's do a little guessing and checking on this one. You're asking yourself, x to what power would go there, so that when you cube it, you get 9. Right? Well, when you simplify this here, you would multiply these two numbers. Therefore, what number does 3 need to be multiplied by to get 9? Well, it needs to be multiplied by 3. So this would be x cubed. Okay, and then here's a tough one, the cubed root of negative 64x to the 6th. Well, you already know that it's going to be negative, because the cubed root of a negative number is always negative. The cubed root of 64, we figured out, is 4. And the cubed root of x to the 6th, you would say x to what power do I put here so that when I cube it I get 6? It would have to be a 2, so that when you multiply that 2 by the 3 you would get a 6 here. So negative 4x squared. Okay, not only can you take square roots or cubed roots, you can actually take 4th roots, 5th roots, 6th roots, and so on, and it just goes on from there. These are nth roots, where n can be any number. So let's look at 4th roots first. Okay, 2 to the 4th is 16, so the 4th root of 16 would be 2. Okay, cubed root of 10,000 sounds kind of hard. Without your calculator, there is a way to do it if you have a graphing calculator. Probably not a simple way to do it on a scientific, but it would depend on what your specific scientific calculator has on it. But really this isn't that hard. Let's just do a little guessing and checking. So let's start with 10. Now if we do 10 to the first power, that's 10. If we do 10 squared, we know that's 100. If we do 10 cubed, remember you just add a 0 each time, that's 1,000. So 10 to the fourth is 1,000 times 10 would be 10,000. So therefore the fourth root of 10,000 must be 10, because 10 to the fourth power equals 10,000. Okay, the fourth root of negative 16 means what number raised to the fourth power is 16? Well, we already know that's 2. So the question is it negative 2, or is it, there's not a real number? So let's see. What happens if we raise negative 2 to the fourth power? Well, you're going to get 4 negative 2's. So these first two negatives cancel, and then the second two negatives also cancel, so you end up with positive 16. Therefore, if you raise 2 to the fourth power, you get 16. Or if you raise negative 2 to the fourth power, you also get 16. So no matter what, because 4 is even, so all these negatives cancel with each other, this is not a real number. And I should say not a real number, because we're going to get to imaginary numbers soon. Okay, the cubed root. Do another cubed root one here. The cubed root of 8x to the sixth. The cubed root of 8, remember, is 2, and the cubed root of x to the sixth would be x squared. And the fifth root of negative 32. Well, 5 is odd, so you can take a negative, or the fifth root of a negative number. You'll get a negative. So you ask, what number times itself 5 times equals 32? It doesn't take long to guess 2, right? If you guess 2, 2 to the first is 2. 2 squared is 4. Times another 2 gives you 8. Times another 2 gives you 16. Oops. Times another 2 gives you 32. So it would be negative 2. And now what I want to do with these is look for some patterns. Okay, we're taking here the square root of 5 squared. Let's do these one step at a time so that you can see why they are the way they are. Now 5 squared, let's first square 5, you get 25. So that would be the square root of 25, which we know to be 5. Okay, so in this one it looks like the square root and the square basically cancel, and that is exactly what they do. Now let's try the same thing, but with a negative 5. Okay, now you have to notice the negative is in the parentheses, therefore we are squaring the number negative 5. So if you do negative 5 times negative 5, the negatives cancel and you get positive 25. And now we're taking the square root of positive 25, well, which is defined to be positive 5. Remember, you always take the principal square root, which is the positive of the square root. Okay, so in this case the square root and the square didn't quite cancel, because if they had just canceled we would have gotten negative 5, but they didn't. Okay, in this next example, cubed root of 2 cubed, 2 cubed is 8, so you'd have cubed root of 8, and the cubed root of 8 is 2. So they did cancel. And in this case, negative 2 cubed is negative 8, and as we know the cubed root of negative 8 is negative 2. So in both of these cases, the cubed root and the cube actually did cancel, and we were just left with what was under, what was inside the radicand, which is 2. Or in this case, the cubed root and the cube cancel, and we were left with negative 2. And the reason is because 3, this 3 right here, is odd. And because you can take odd roots of negative numbers. Okay, so let's generalize. If n is an even positive integer, okay, this n, meaning the nth root of a to the n. So in this case, first example, we did squares. Well, 2 is even, right? 4 is also even, so 4th root of 5 to the 4th. Let's do another example down here. 4th root of 5 to the 4th would be 5, and 4th root of negative 5 to the 4th would also be 5. Okay, So what it looks like it is it's the nth root, the pattern here, of a, where a can be anything, to the n. Actually, what you do is you make it positive. So if you start with this positive 5, your answer is positive 5. But if you start with negative 5, your answer is also positive 5. Well, you think, what's the thing that makes everything positive? Well, that's absolute value that does that. So this is equal to the absolute value of a, because you make what's on the inside positive, that a. But if n is odd, so for example, cubed roots or fifth roots or seventh roots, then you actually do include that negative. So if a is negative, you would just keep it negative. So therefore, they do just straight up cancel the nth root and the nth power. So you just get plain old a. Okay, for the most part, you could just do this one step at a time the way I did, and it's not going to mess you up, at least not in this class. This really comes in handy in college algebra, and after that, if you're simplifying with or pre-cal, if you're simplifying with and you have variables, the absolute value bars become very important there. Okay, so let's do a few examples. Here we have the square root of negative 4 squared. Well, because we're taking square roots of something squared, we happen to have the same index as we do power. Let's do this in blue. So we have the same index as we do power. This is going to be the absolute value of negative 4 using the shortcut rule, which is 4. Okay, or you could have just squared negative 4 and got 16, then taken the square root of 16 and gotten 4. Either way, you'd get the same thing. Okay, and this one over here. Now this is not written in the form nth root of a to the n, because we have a square root here and then we have a power of 6 over here. So in order to use these rules, which is what I want to do, we need to rewrite what's under the radical as something squared. Okay, so I'm going to rewrite it as x cubed all squared. Okay, now the a, this a, corresponds to x cubed, because that's the thing that's being squared and taken the square root of. Okay, now 2 is even, that index 2 is even, therefore it's the absolute value of what's on the inside. So we would actually have the absolute value of x cubed. That's the technically correct answer here. On this next one, we have fourth root of x plus 6 in parentheses, all to the fourth. Okay, now x plus 6 is all in parentheses, so we can treat it as its own quantity. Now we're taking the fourth root of something to the fourth. 4 is even, therefore we're going to use the absolute value rule. So it would be the absolute value of x plus 6. Now you have to keep those absolute values on both of these previous problems, because if x is negative, those absolute values are needed. Now if x is, for example, if x is negative 10, say down here you'd have negative 10 plus 6, which is negative 4. So the absolute value bars are very important, because sometimes they're needed depending on what x is, and sometimes they're not, but you would have to make that negative 4 positive. So absolute value bars are important if you're dealing with variables especially. Okay, here we have the cubed root of negative 3 all cubed. Okay, cubed. 3 is odd, so there are no absolute value bars. The cubed root and the cube simply cancel, and we just get negative 3. In this one, we have a fifth root of 7x minus 1 all to the fifth. 5 is odd, so there are no absolute value bars, so we just have 7x minus 1. And in this one, we have square root of 36, x to the squared. Okay, so we need to rewrite it as something all squared in order to apply these rules up here. Right, the way it's written, the square only applies to the x, but it's not applying to the 36. So let's actually rewrite this as 6x all squared. Okay, now I'm not changing the problem, I'm just rewriting it so that we have a square root and a power of 2. So our a corresponds to 6x. Now 2 is even, so technically this would be the absolute value of 6x. Okay, this last one is also not written as something all squared. And this is a bit of a tough one, but you can do it. You just have to rewrite this trinomial as something squared. Well, we know trinomials, if they factor into a product of two binomials. Hopefully this one's a perfect square binomial. So let's see, is there x, we have all positive, so we'll have a plus. X plus something all squared that equals this. Well, looks like if we do x plus 3 all squared, we would get, let's see, let's write it out. If we FOIL, we get x squared for the first terms, 3x for the outside terms, and 3x for the inside terms, and 9 for the last terms. Okay, so we can rewrite this first as the square root of x plus 3 all squared. Now the square root and the square cancel, except because 2 is even, we have to have some absolute value bars. So it's the same as the absolute value of x plus 3. So that's a surprising simplification there. Okay. Go back to the examples that we did previously and see if there are any that we actually need to fix that involve variables, okay, that to odd roots, variables with odd roots and odd powers that we might need to add some absolute value bars on. Okay, so I'm scanning all the problems we did for ones with variables, because if it didn't have a variable, then our answer would certainly be correct, because the way we did it, we would have just squared the number or cubed the number first and then taken the cubed or square root, so we would have ended up with the correct answer anyways. Here's one right here. And now this one doesn't look like we could easily rewrite it as something all cubed. Oh no, I take that back, we can. What am I saying? We could rewrite the 8x to the 6th as 2x squared all cubed, because 2 cubed is 8 and x squared cubed is x to the 6th. Now we have cubed root and a cube here, so they simply cancel and you get 2x squared. There's no absolute value bars because 3 is odd. So that one was correct already. Going back up, this one too has a variable in it. However, we know that our answer is correct again because 3 is odd, so there's going to be no need to add any absolute value bars. Same thing here, 3 is odd, so no need to add any absolute value bars. Okay, going back to these original examples, we did 2 here that have variables. Okay, now this one, square root of x to the 10th. We could rewrite this as square root of x to the 5th all squared. Now we have the square root of something squared, and 2 is even, so they cancel and we get x to the 5th, but we actually need absolute value bars. So technically you should go add some absolute value bars onto your answer. Now that's important because if x is negative, for example, if x is -2 right here, and you plugged in a -2, -2 to the 5th is -32. But if you plug it in here, the correct version, -2 to the 5th, you get -32. Then you take the absolute value and you get +32. Now I know that's correct because if I plug in -2 here, I would first raise it to the 10th power, which would make it positive. Then I would take the square root of a positive number, which would be positive. So we would want our answer to always be positive. Therefore, we need absolute value bars on that one. Okay, let's check this one as well. Square root of 36x to the 6th. We could rewrite that as square root of 6x cubed all to squared. Now the square root and square cancel, but because 2 is even, we need absolute value bars, so that would be absolute value of 3x cubed, of 6 times 3x cubed. Now technically you can pull the 6 out because it's already positive anyway, so you'd have 6 times the absolute value of x cubed. So technically we need to add some absolute value bars here, okay, and to make sure that this works. Okay, now let's go on to this last and final section of this chapter. Part of this section, last and final part of this section. Okay, and that is radical functions. All right, you can define a function in terms of radicals. For example, you could let f of x equal square root of x plus 2, or g of x be the cubed root of x minus 1. So with these, let's do a little bit of practice and find some numbers here. Let's find f of 7. F of 7, that would mean plug in 7 for x on f, so that would be the square root of 7 plus 2. And then from here you just go one step at a time in the order of operations. So square root of 9, so you get 3. F of 0 would be plug in 0 for f, so that would be square root of 0 plus 2, or the square root of 2, and then you go, wait a minute, square root of 2 is not a perfect square, so that's not a rational number. There's no easy way to write it. So in fact, actually the simplest exact way to write this answer is to leave it like that and just say square root of 2. You could approximate, but then it wouldn't be exact because square root of 2 is irrational. So typically ones like that, if you can't simplify it, you just leave it as the radical. Okay, we don't typically approximate unless we're working some sort of applied problem where you need a decimal number. Square root of negative 4, or f of negative 4 would be the square root of negative 4 plus 2. Well, that would be the square root of negative 2, and that is, as we know, not a real number. But I would go ahead and circle the negative square root of negative 2 part as well, because you'll see why that's important later on. Okay, let's look at g. G of 9 would be the cubed root of 9 minus 1. That's the cubed root of 8, which you know to be 2. G of 10, that would be the cubed root of 10 minus 1, or the cubed root of 9. Now the square root of 9 is 3. 9 is a perfect square, but 9 is not a perfect cube. No number cubed equals 9 exactly, so this actually cannot be simplified. That is what it is. And g of 0 would be cubed root of 0 minus 1, or the cubed root of negative 1, which we know to be negative 1. Negative 1 cubed is negative 1. Okay, so that's just using radicals as functions. Now let's graph a radical function, and see what it looks like. This is where it gets pretty interesting. Okay, I want to graph f of x equals the square root of x minus 1. So to do this, let's make a t-chart. And plug in lots of numbers here. Okay, I'm going to go from left to right. I'm going to start at some negative numbers of x and then go to positive numbers of x. And these graphs here should be aligned so that you can nicely fit the graph in. So let's start at, let's just say, negative 8. Let's see what happens there. If we do negative 8, we would get the square root of 8 minus 1. Well, that's, square root of negative 8 minus 1, which is the square root of negative 9. That's not negative 3. Square root of negative 9 is not a real number. I'm just going to write NaN for abbreviation. So that means you cannot graph it because you don't get a real number. There's nowhere to plot it. Okay, and so you can quickly tell if I plug in other negative numbers that are pretty big, same thing's going to happen. So let's jump down to negative 2 because I don't want to miss anything, just to be on the safe side. If I plug in negative 2, I get negative 2 minus 1, which is negative 3. Okay, still not a number. So let's go up to 0. If I plug in 0, I have square root of 0 minus 1, which is square root of negative 1. Still not a number. Alright, so let's try 1. If I plug in 1, we have square root of 1 minus 1. That's the square root of 0, which is 0. Okay, that's the first point that we can plot, is 1, 0, right there. 1, 0. Okay, let's try the next number. Let's try 2. If we do 2, we'd have square root of 2 minus 1, which is the square root of 1, which is 1. Another point we can plot, 2, 1. So let's try 3. Square root of 3 minus 1 is the square root of 2. Now that's not exact, but because we're plotting, we would need to approximate that. Square root of 2 is about 1.41421. Let's just round to 1 decimal here because I'm not going to be able to plot more accurately than that anyways. So 3, 1.4, somewhere in there. And then from here on out, I'm just going to pick numbers that will give me perfect squares under the radical so that I don't have to approximate. So you'd say, okay, the next perfect square is 4. What number x do I need to plug in so that I get a 4 under the radical? Well, that would be 5 because we're taking 1 away from it. So if we take 1 away from 5, we do get square root of 4, which is 2. So that's an easy one to plot. The next perfect square is 9, so I would need to plug in 10. Square root of 10 minus 1 does give me square root of 9, which is 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so you can see it's kind of flattening out here quite a bit. Let's see if we can do one more perfect square. Not sure if we can fit it in here. So let's do 16. So we need to plug in 17 to get a 16 under the radical to get a y value of 4. Let's see if that's 9. That's 10, 11, 12, 13, 14. I can't fit it on my graph. You can probably fit it on your paper. But as you can see, the graph started right here. That was the first point we got. And then it just really slowly increases. And that's exactly what radical functions look like. They tend to only cover half the plane because any x values over here give you not a real number. So radical functions tend to only cover half the plane. And they tend to be kind of flat. Now technically they never flatten out. This actually does go up forever and ever. Although it looks like it gets horizontal, it never quite gets to horizontal. It actually increases forever. So there's your first radical function. Okay, let's graph a different one. This one's a cubed root, so it's going to look a little bit different. Okay, h of x equals the cubed root of x plus 2. So again, let's make a t-chart. Okay, and this one again, let's plug in some negative numbers and positive numbers both. Want to make sure we cover everything. So let's try negative, let's see, I'm thinking negative 8. If I plugged in negative 8, I would get negative 2 for this radical anyways. The next perfect cube, let's see, 2 cubed is 8, 3 cubed is 27. I don't think I can go out to 27 here, so we'll just stick with negative 8. Okay, so we would have the cubed root of negative 8 plus 2. The cubed root of negative 8 is negative 2. Then plus 2 gives me 0. So I have negative 8 comma 0. Right about there. Okay, then we'd have the next perfect cube is 1. I may want to plot another point in between negative 8 and negative 1 because that's such a big jump, and I'll just approximate it on my calculator. So let's try negative 5. Okay, the cubed root of negative 5 plus 2. Let's see, approximating that on my calculator. How do you do cubed roots on your calculator? It depends on your calculator. We're gonna learn one way in a section coming up that will work on all calculators. If you want to enter something directly as a cubed root, there may or may not be a button for it at this point. So, but I guess I need to go ahead and show you the shortcut in case your calculator does not have a cubed root function. So the way you can always enter it on any calculator for cubed roots, so you want to enter cubed root of negative 5. That's the same as negative 5 to the 1/3. Okay, this 3, that cube, has to be the same as that denominator there. And it's always 1 over that index. So you would do negative 5 to the power of, this is how you would enter it, negative 5 to the power of parentheses 1 over 3. Depending on your calculator, you basically want to enter that, although how you enter that exactly may not be in that order, so you might have to look at the manual for your particular calculator. But mine says that that is approximately negative 1.70998. So make sure you can get that on your calculator and you'll know you're doing it right. Okay, then we would want to add 2 to that. So that would be approximately 0.29 or 0.3. So if I got to negative 5, that's about a third of the way up. Okay, not much. Alright, so let's jump to the next perfect cube, which is 1. Negative 1, I mean. So cubed root of negative 1 plus 2 would be negative 1 plus 2, which is 1. So now if I got to negative 1, I go up to 1. So far this is not looking like much. It's just looking kind of like a line. But it's not going to be a line, okay? No cubed root or square root or any radical function will ever be a straight line. There's always going to be some bit of a curve to it. Let's try 0 because that one looks easy. Cubed root of 0 is 0. Plus 2 is 2. So 0, 2. And there we can see it's starting to get some curvature to it. Let's try 1. Cubed root of 1 is 1. Plus 2 is 3. I'm just going to do these in my head. Next perfect cube would be 8 again. Cubed root of 8 is 2. Plus 2 is 4. So 1. Need to go to 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. Okay, so you can see kind of what it's doing. It's pretty flat. Looks like it's flat, 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 and then it curves a little here, and then it kind of flattens out again. Now, it doesn't exactly go horizontal, remember. It does go down forever and up forever very, very, very slowly. So what's different about this graph, you may notice, is that it covers the whole x-axis, and that's because you can take a cubed root of a positive or negative number, or if any index is odd, so 5th root, 7th root, 9th root, and so on, will actually cover the whole domain. You can plug in any x and get a number. However, with square roots or any index that's evens, 4th roots, 6th roots, 8th roots, they'll look kind of like this and only cover half the plane. So their domain does not include any x's that give you a negative under that radical. Okay, so let's generalize what I just said. If n is a positive integer, let's say if n is even, okay, then the domain of the nth root of x is only positive numbers. It would be the set of all x such that x is greater than 0. Greater than or equal to 0. Square root of 0 is 0. Or in interval notation you could say from 0 to infinity. Okay, but if n is odd, so cubed root, 5th root, and so on, you can take the nth root of an odd number, so the domain would just be all real numbers, or from negative infinity to infinity. Alright, so it's a good idea to know what the basic graphs look like, and then from there you can transform them and use your knowledge of the basic graphs to get an idea of what the transformed or slightly off graphs will look like. Square root of x will start at 0, 0 because that's the first number in the domain. Square root of 1 is 1. Square root of 4 is 2. Okay, so its graph looks basically like that. Cubed root of x is similar. Cubed root of 1 is 1. Cubed root of 8 is 2. So it would be about up here. And then cubed root of negative 1 is negative 1, and cubed root of negative 8 is negative 2. So its graph looks more like this. Okay, the domain of this first graph we drew, as we said before, it's from 0 to infinity, including 0. And this one goes from negative infinity to infinity. Now let's do a 4th root and a 5th root so you can see the difference. For the 4th root of x, we cannot take the 4th root of any negative numbers, so we just start at 0. So its domain is going to be from 0 to infinity. And 4th root of 1 is 1. The next perfect 4th root, okay, 2 to the 4th is 16, so it's way out here, way off my graph. So basically it's just flatter is the only difference between the 4th root and the square root. As you can see the way I drew it, it's just a little bit flatter. Same thing for fifth roots. Fifth root of 0 is 0, fifth root of -1 is -1, and fifth root of 1 is 1. Those 3 points are the same basically regardless of what the index is. But then after that, okay, the next perfect fifth root would be 2 to the fifth. 2 to the fifth is 32. So the fifth root of -32 is -2. That's way out there. So this gets really, really flat immediately. In fact, that's probably even too steep right there. It's bit flatter than that. It's technically not exactly flat, but it appears like it. So the higher the index, the flatter it gets, and that's what the shapes look like. So that is it for the first section of Chapter 10 with radicals and radical functions. Join in next time for Section 10.2.